Right, this is video 6 in the probability section. This is basically this is a combination of events. A lot of these problems are kind of about balls being drawn out of bags, and very often, if they're not balls being drawn out of bags, you can model the problem by balls being dragged, being brought out of bags. So it's the topic is called combinatorics. Um, so it's got some kind of quite interesting but tricky problems in it. Yeah, let's just have a look at some examples, and that'll illustrate what we mean. Okay, now this video is the typical scenario. Here is we've got balls in a bag, and we take them out, and we don't put them back in. You usually take another one, maybe another one after that, but we're not actually replacing them. So the maths is a little bit different to the situation where we would actually put them back, and they would all be there ready for our next selection. Okay, so envisage that situation. We're drawing balls out of a bag, we don't replace them. So here we go. An urn has 6 red balls and 4 green balls. All right, it's an urn, not a bag. All right. These are extracted without replacement and placed in a row. How many different arrangements are there? Okay, so what we do, imagine we've got a little kind of template with 10 slots in there. We pick one ball out, we put it in the first slot, another ball put in the second, and so on. So there are 10 balls. Now, if we were to imagine, first of all, that these balls are numbered, so they are actually different. So there'll be 6 red balls numbered 1, 2, 3, 4, 5, 6, and 4 greens 1, 2, 3, 4. So when we take the first one out, there's one of 10. It can be any one of 10 balls. Put it in the first slot. Second one, there's 9 left, so it can be therefore the next can be any one of 9. So that goes in the second slot, and so on. So as we continue that process down to the last ball, the number of different arrangements, if we're interested in the numbers on the ball, would be 10 factorial. That's 10 times 9 times 8 times 7 times 6, all the way down to 1. That's what factorial is. It means 10 factorial. Okay, so, and this would be here's an example. Here we've got written down R4, G3, R1, R6, G2, and so on down to G4 there. So that would be 10 factorial different ways. Now, the thing is that when we say how many different arrangements, and we're not told that these balls are numbered, so if we happen to get a similar arrangement in terms of reds and greens, but the numbers were different, then as far as we're concerned, that would be the same arrangement. We wouldn't be able to spot one red ball from another. Okay, so in actual fact, in terms of the number of arrangements, this 10 factorial overcounts because it's counting the same arrangement, but with the numbers in different places more than once. So we have to factor that out. So we have to divide through by the possible number of arrangements of, first of all, those red balls. Well, there are 6. So if you can imagine that the slots that have actually been occupied by the red balls, we can arrange these 6 into, well, it's a similar problem, isn't it? If we take the red balls out and put them back into those red slots, this for first, third, fourth, and so on, then there would be 6 different balls that we can put into the first one. That's there. 5 into that, 4 into that, 3 into that, 2 into that, and 1 in that. So that would be 6 factorial. So we're kind of factoring back out the fact that we've actually counted 6 factorial times too many. So that would be that 6 factorial there. And then again, we're going to do it for the greens as well. So that would be that 4 factorial. So that would actually be the total number of different arrangements. So this always works out as an integer, by the way. When we cancel. We can imagine that 6 factorial will knock out the last 6 of the here, so that will be 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1, and that's going to work out to be an integer. And this is this number here we would tend to note as 10. Well, we call it 10 choose 6. It's obviously the same as 10 choose 4, isn't it? And sometimes we write it like that. Sometimes we write it like that. Sometimes we write it like this. It's a sort of vector, I suppose. So different ways. And there are a few other different notations, but they all mean the same thing. 10 choose 6. And just at this point, just to mention, there is, if we are interested in the arrangements of the well, in this case, it would be of the greens, for instance. If the greens were numbered but the reds weren't, it would be 10 perm 4. That's the vernacular we use, 10 permute 4, and that would be 10 factorial. We only have to factor out the 6 red ones. Doesn't come into the questions quite so much, wasn't this, but just worth knowing about. So that's basically how that works. So I want to have a look at sort of a development of this particular problem. Another urn has 10 red balls and 6 green balls, 16 in total. 10 are extracted and without replacement and placed in a row. Same thing, basically. How many different arrangements are there that have 6 red and 4 green? Now, there's slightly tricky thinking on here, because what we actually need to do is we need to imagine that we've taken all 16 balls out and arranged them. And what we've got here, therefore, is we've got these are the 10 balls. These are the 10 that we've extracted and placed in a row. Okay, and these are the remaining ones that we've just taken out. Okay. So the total number of arrangements essentially is this. This is the same as before, isn't it? 10 choose 6, 10 choose 4. And then we've got these remaining ones, because basically we've got 6 slots here. So 6. We've got 4 reds and 2 greens. So that would be the total number of arrangements that have 6 red and 4 greens. Yeah. So all this lot, the total number of arrangements that have 6 red and 4 greens. So let's just scroll a bit. How many arrangements? How many arrangements are there of the whole urn of 16 balls? Well, if we just look at the whole 16 and just imagine them in one template with 16 slots in, then it would be this. So that would be the total number of possible arrangements of the 16. Okay, so that's what we've got there. So then the question that's kind of then leads to, let's scroll up there. If you extract 10 balls from an urn with 10 red and 6 green, what's the probability of getting 6 reds and 4 greens? All right, so if we reform this as arrange the 16 balls left to right, the first 10 are our extraction, then the probability is equal to the total arrangements with 6 red and 4 greens, which of course is this. Times the total arrangements with 4 reds and 2 greens. So that's that times that, divided by the total number of arrangements with 10 reds and 6 greens into 16 different slots. So that's our 10 choose 6, that's our 6 choose 4, and that's our 16 choose 10. Okay, so that is that probability. No, so basically we just work all this lot through here, and there's quite a lot of cancellation goes on. Then essentially that's it. Is it the probability 0.39323 decimal places? That's quite a tricky problem actually. But I think it's quite important that you kind of understand that line of thinking. If I'm perfectly honest, I wouldn't worry too much about it. I think you'll be unlucky to get a problem like that in an examination. Um, but I think it is actually quite useful to understand how it works. And I think a lot of the thinking is, a lot of these problems are you can model by balls and bags, or balls and urns, if you like. Okay, so that's it. Now I've already said these things. 10 choose 6. That's the phrase that we use, and there's different notations. 10 choose 6 is the same as 10 choose 4. And basically it's always a whole number. And just in case it corrupts, 0 factorial and 1 factorial are both equal to 1. 0 factorial takes a bit of thinking about why that is, but anyway, you can just take that as read. That is 1. A few other sort of combinatorial problems here. These are probably slightly simpler than that last problem. Well, they are definitely. If it matters what order the ones we choose fall in, then we use 10p6, as I mentioned above. In other words, we don't factor out the 6. Let's have a look at this. A pizza place offers 14 different toppings. How many different 3-topping pizzas can you order? Well, this is basically 14 choose 3. You've got 14 to choose from, and you choose 3. Another bit of slightly different notation there. 14 choose 3 equals 14 factorial over 3 factorial times 14 minus 3 factorial, 11 factorial in other words, and that's 364. So be spoilt for choice if you go to that place. How many ways can we divide 16 players into 2 teams of 8 members? Right, okay. Yeah, so it's basically what we're doing is we've got our 16 slots. The first 8 slots are one team. The second 8 slots are another team. So we've got 16 choose 8, which is 16 factorial over 8 factorial times 8 factorial. A lot of cancellation, and eventually we come out with this 12,870 different teams. Obviously, once one team's decided, then that the other team is decided. So that is some kind of illustrations of how we use the choose function. So hope that's useful. We're coming on next to what happens if we actually replace the balls in the urn. It gives us a slightly different scenario, and one which actually then comes into the binomial coefficients and binomial probability and lots of other things like that. Okay, so good. Hope that was okay. I'll see you next time.